So good morning, and of course, let me add my thank you to Andrea and the team. This is a truly amazing thing and portent of things to come, I hope. So I'm going to talk about far ultraviolet C light, which we hope is going to prevent the airborne transmission of the SARS-CoV-2 virus, but also all other viruses. It's not specific to SARS-CoV-2. So we know that one of the main transmission modes for COVID-19 is airborne transmission, as well as touching. And the airborne carrier particles have quite a big range in size. The big ones are microns in size, small ones are submicrons. And I hope you can see a simulation from KIT in Japan, somebody sneezing, and the larger particles, which are the blue and the green particles, within a minute or so are falling to the ground. But the smaller particles, the aerosols, are not. So here's the same simulation, just looking at the smaller particles and over a time scale of a few minutes here. And you can see over what will be 20 minutes, I think. The smaller particles are still in the air. And importantly, what we now know is that there have been some good studies of the SARS-CoV-2 virus stability, which finds viability in these aerosols for several hours. So these aerosols potentially have viable virus in them. So the question we have is, how can we inactivate these airborne viruses in occupied spaces, like in the last picture? And let me start by saying that we actually know how to kill every possible kind of microbe, bacteria, viruses. And that's with ultraviolet light, and we've known that for more than 100 years. You know, it's used broadly. Here's an operating room which is being decontaminated overnight with conventional germicidal ultraviolet light. But what you might notice from this picture is that there's nobody in it, and that's the issue with conventional germicidal UV, that it's a health hazard. It causes skin cancer, causes eye diseases. So while you can use it when people aren't around, you can't realistically use it in populated locations. So working from that as our basis, we started to think about Far-UVC light, and specifically that's at the far end of the ultraviolet spectrum, illustrated here. And it's around 220 nanometers in terms of wavelength. And what happens in that region is that there is a large protein resonance around there. And what that means is that light at these wavelengths has very limited penetration in biological materials. It gets absorbed very quickly in any sort of protein or similar molecules. So what does that mean? Well, this is a little simulation. So here's our skin. Here, right at the top, we've got the stratum corneum, and below the squamous cells and the basal cells and the melanocytes. So, and here's my notion of what microbes look like above in the air. So with conventional germicidal UV, I mean, what happens is, because the UV is very penetrating, well, it's killing the bugs, but it's also producing damage in the squamous cells and the melanocytes. So we know it causes squamous cell carcinoma. We know it causes melanoma. But let's contrast this with the situation with Far-UVC light, which has a very short range, but certainly enough range to penetrate a virus or a bacteria. So what you see is that the Far-UVC light potentially can kill the viruses and bacteria just the same way, but it can't penetrate anywhere near the stratum corneum, the dead cells and the surface of our skin. So it can't damage any of the healthy cells, or the living cells, I should say, in our skin. And the same applies to the eye, where we have a tear layer that does the same thing. So that's encouraging that, in principle at least, Far-UVC light has the same germicidal properties as conventional UV, but is potentially safe. So the two questions that we've been asking ourselves are, first of all, most importantly, is it safe, and does it work? So in terms of safety studies, well, we've started with in vitro laboratory studies. So we use human skin models with a stratum corneum, an epidermis, and a dermis. And what we plot here is the two conventional pre-malignant assays that people in the UV world look at, and as a function of UV fluence, both for conventional germicidal UV, which is here, so there's a good dose response here, and for Far-UVC light, where basically you don't see anything in the any damage in the epidermis, and that's because all the light is absorbed in the stratum corneum. In vivo, well, we're actually in the midst of a big study, and happily our mice are still alive and in the one of our facilities. So this is a 60-week year, 15-month exposure study with 100 hairless mice, and they're being exposed to pretty high doses of Far-UVC light, 8 hours a day, and we examine them every week or so for skin lesions and give them eye exams. And we're about 38 weeks into this study, doing different doses, males, females, and we see no skin lesions and no eye damage at all as yet. So again, pretty encouraging. But again, that's what you expect purely on the basis of the physics. That this is basically a physics-based approach, that the Far-UVC light simply can't reach living cells. So those are the safety studies. Well, what about the efficacy studies? Well, we're primarily interested in airborne virus. So we set up this apparatus. So we aerosolize viruses on the left here, flow them through this exposure chamber here. And this is a Far-UVC light, which I turned around so that you can see it, but it would normally be facing the exposure chamber. And then at the far end, we have a biosampler, and we assay how many viruses are alive or dead. And what you see on the right-hand side for two of the seasonal human COVID viruses, an alpha virus and a beta virus, that they are actually very sensitive to Far-UVC light. And we'd actually done this study earlier with H1N1 influenza and got pretty well the same results. So with very, very low exposures here, we're getting 1, 2, 3, 4 logs of killing. So yeah, it's certainly effective in inactivating aerosolized coronavirus. And the study that we were about to start, and we'd finally got all our IACUC approvals and so on, but then the COVID-19 hit, was to do a direct transmission study. This was going to be with influenza, with H1N1, and jointly with Mount Sinai. So basically we have two cages which are separated, but there is airflow in between them. We have a donor guinea pig, which we give influenza to, and then we have a recipient.
David, you have 1 minute left.
Okay, I think I'm good. And then we have a recipient guinea pig on the left here, and we assay whether or not that gets influenza, both without lamps and with lamps. So that is a direct assay of whether the technique would work. So in the near future, I mean, we see Far-UVC light ubiquitous in occupied public spaces, and there are a couple of companies now that are ramping up big time, and their claim is in 6 to 9 months they will be producing many hundreds and thousands of these lamps, which can simply be installed where in public places in the same locations where the conventional lighting is overhead. So we can see it certainly in public transportation systems, trains and planes and so on. We can see it in airports, which would be great for preventing pandemics. We see it in schools. Our original notion was preventing the spread of measles in schools, but again, this approach would work for concurrently for all viruses. So I think there is a good future here. We need to get through the FDA approval for this, and we need to ramp up the production of lamps into the hundreds of thousands and the millions. So there I'll stop. I think my time is up, and again, happy to answer any questions.
Yes, we can hear you.
Great. I was wondering how you're testing the damage to the eyes in the mice.
Well, they're being given eye exams initially it was every week, and now they're being given eye exams every 2 weeks, and that's with Norm Kleiman from the Eye Institute.
So if you're interested, we also have an instrument where we can assess their cornea and retina, in the future when we're out of this pandemic, that might be useful. And
that would be great. There are clearly these two issues of the skin and the eye. We have great models for the skin. We could certainly do with more help in the eye, so thank you.